Welcome to Why So Spurious. Why So Spurious? This is a presentation on a hardware feature that exists in Intel and AMD chips. And operating system developers didn't, so the instruction manual, there's hundreds of tiny little tidbits in this, and there was a tiny little bit that they missed, and we actually used this to create an exploit, to create an LPE. And spurious essentially means unexpected. So it's an appropriate name, followed by Batman. These are our presentation topics. We're going to go through introductions. I'm going to introduce myself, and then my colleague Nemanja is going to introduce himself and his background. Then we're going to go over what is CVE 2018-8897. If you don't know what a CVE is, hopefully by the end of this presentation, hopefully you'll know what a CVE is. We're going to go over some prerequisite knowledge. Nemanja is going to kind of train you on some high-level information that you need to actually understand how this works. Granted that we only have 50 minutes. It's important that you keep in mind that we have a white paper if you actually want to understand a lot of the deep technical details of how this works. We have a link to that at the end of this presentation. After that, I'm going to go over how move SS and pop SS actually function, what they do, why they're special in the x86 architecture. And then we have 3 proof of concepts. It's kind of in order how special they are. The first one is a local denial of service. It just kind of just blows up your own machine. It's not really that incredible. The second one is a local privilege escalation using int3. This is the one that I personally weaponized. It's my personal favorite. And then we have the second one, local privilege escalation using Syscall. That's the one that Nemanja here weaponized himself. That one's also incredible. And then we have a conclusion. At the end, there's a couple heads in the industry that we'd like to give shout outs to. People who weaponized it, people who actually gave us some input during this entire process. And some really cool people we'd like to give thanks to. So, I'm Nick Peterson. I got my start in this at a really young age in gaming. World of Warcraft, actually. I played hardcore through high school. In fact, I almost dropped out raiding all the time. I'm sure if you're in this crowd, you've probably played World of Warcraft at some point. If you haven't, I'm sure you at least know what it is. I started, while playing World of Warcraft, I did a lot of teleport hacks, bots, and morpher hacks, sort of vanity-based skin modifications that you could do to the game. I sold some of that stuff, some of the other stuff I didn't. After that, I started a cheat site called Subtle Aim, which I sold subscription-based Counter-Strike Global Offensive cheats to, where you would basically pay me a monthly subscription to cheat in Counter-Strike Global Offensive, and you would get access to an aimbot and an ESP, and as long as you paid me $25 a month, you would be able to keep cheating in the game. After that, I was hired into Riot Games by Nemanja, actually seeked me out, where I currently do similar work. Currently working on League of Legends. We deal with a lot of cheaters there and working on future products. So I'm going to go ahead and hand it over to Nemanja.
Awesome.
Introduce himself. Here you go.
Cool. Thanks, man. So, yeah, I actually started very similar to Nick. I was game hacking when I first, got into information security, and I actually got my start in the same game, World of Warcraft. I guess it was a popular game at the time, and that's where I first really began, game hacking. And what ended up evolving was I guess, passion for security. I worked in the government for a couple of years, and then decided that it was very bureaucratic, and I didn't want to stay in that business for long. So I looked to the West Coast to find a job in gaming, because that was really where my passion started in this field. I worked at Blizzard Entertainment for a couple of years. I worked on Overwatch's anti-cheat, which is a popular first-person shooter game. Then from there, I moved to Riot, and now I work with Nick on League of Legends. So to understand really what CVE 2018-8897 is, we have to explain what it could do, right? So this CVE is a local privilege escalation vulnerability. It allows you to read and write kernel memory from user mode, and it also lets you execute user mode code with kernel mode privileges. So it's pretty crazy. Like, it gives you full compromise on a system that you're on. And it impacted a ton of different operating systems, not just Windows, which a lot of the demo code will focus on just because it's the most prevalent operating system, but it also affected Linux, macOS, FreeBSD, and even Xen configurations. Basically anything that was x86 based probably fucked up in handling how move and pop SS worked. To really understand how this works, you have to kind of know how interrupts function and how hardware breakpoints work. And we'll go over that knowledge. This is assuming that you already have a good understanding of assembly. You have to have some level of assembly knowledge. I'm sure a lot of you have done reverse engineering, whether it's malware or maybe even game hacking. So hopefully with this additional knowledge, you'll really understand how the core OS functions when it encounters some of these behaviors. Now, everyone's seen this probably a million times. I'm sure other Black Hat presenters actually use the same picture of the privilege levels on an operating system. It's just on Wikipedia. And really, in the traditional sense, there's only ring 3 and ring 0. Ring 1 and 2 are really never used. Ring 3 is where the untrusted user mode applications execute. These are your games, your favorite calculator.exe that gets popped all the time, as well as, basically anything that you interact with directly as an end user of that system. And then as you transcend into these rings, you start gaining more and more privileges. You can use more functionality of the operating system. And ring 0 is intended to be the most privileged arena where the kernel operates and where the core OS features are. Now, this gets complicated, obviously, with hypervisors as well as like Intel Management Engine, but to our presentation, this is the simplified view and how things were a decade ago. When a hardware breakpoint fires, it's super important to understand that, and there's charts here that you don't really have to look through. This is in the SDM, the Intel Software Development Manual, so you could browse this at your leisure when you're trying to fall asleep. But the software breakpoint is different from a hardware breakpoint. I'm sure a lot of you guys have used software breakpoints for debugging purposes. Software breakpoint is an int3 or a CC, and hardware breakpoint varies from that in that I'll use the term data breakpoint interchangeably to mean hardware breakpoint. There's only 4 of them on the x86 architecture. You can set them on access, read, and write. You only get 4 per processor. Every processor has its own view of hardware breakpoints. When a hardware breakpoint occurs, or when any interrupt fires, not just hardware breakpoints, execution is given to the kernel by the CPU, and we'll explain how that process works, but there's certain status bits in some other debug registers that explain what tripped and exactly how you can control these hardware breakpoints. The most important thing to note is really that this is a privileged thing. You can't just set hardware breakpoints from user mode, but most operating systems provide a way to do that through APIs that will just issue system calls under the hood. In Windows, you can do this by using setThread context, and other operating systems do it differently, but most offer this for any application that runs. It doesn't have to be an administrator application just because it's such a powerful debugging tool. So when an interrupt fires, an int1 fires, a DB fires, the CPU transfers execution to an interrupt handler. And this interrupt handler is located inside of this giant lookup table, this IDT that gets set up early kernel initialization by the operating system. So based on what interrupt fires, it's the index inside of this IDT. So for hardware breakpoints, it's int1, and that is the second index, assuming you start at 0. And int3 is the 4th index, which is where your software breakpoints are firing. So when an int1 or an int3 fires, the CPU will look at its interrupt descriptor table to figure out where to go in the kernel to process that interrupt that's fired. These are all the interrupts on Windows. Not super important to note all of them, just that the int1 handler, which is the one for hardware breakpoints, it's called KI-debug trap or fault. Additionally, when that int1 fires, there's some stacks artifacts that are pushed on by the CPU, and this is mostly so that your kernel mode handler that's handling this interrupt knows where it came from. So there's certain stuff that's placed onto the stack, like the instruction pointer where the interrupt was fired, the code segment to figure out what previous mode of execution it was. In that, is it coming from user mode? Is it coming from kernel mode? There's flags, the stack pointers, and so on and so forth. And traditionally, for mostly every single operating system we've looked at, the OS interrupt handler, KI debug trap or fault, for example, for the int1 handler in Windows, looks at this code segment selector on the stack to determine what the previous privilege level was, where the code's coming from. Is it coming from kernel mode? Is it coming from user mode? And the first 2 bits in the CS value actually tell you what mode it is, and we'll actually explain how that looks a little bit more. To really understand how segmentation works, it's complicated. It's not really necessary for 64-bit mode. It's kind of a vestigial part of the x86 architecture. The reason why I bring it up is because there are going to be callouts to certain segment selectors that you need to be aware of. Like, for example, the CS is the code segment that gets placed onto the stack by the CPU when the int1 fires. Then there's the stack segment selector SS, which is the move SS and the pop SS part. And all of these segment selectors are just indices inside of this global descriptor table, very similar to an IDT set up during early kernel initialization. Describes kind of how that region of memory works. Because paging exists nowadays, it's super irrelevant. What operating systems still use are FS and GS segment selectors, and the reason for that is because they actually, you can set arbitrary base addresses still in 64-bit mode. That means, like, assuming I'm an OS developer and I want to read like kernel mode data structures, I can actually, set a base address of, for example, FS to be 12345. So when I read FS 100, I'm actually reading from FS, or from the linear address 12445. And again, as I mentioned earlier, the first 2 bits of the segment selector index explain what privilege level you're coming from. So whether you're coming from kernel mode or user mode. So, and as an example, so that you understand that, a CS value of 10 and 13, hex 10 and hex 13, describe the same index inside of this GDT. One describes a kernel mode segment selector, the other describes a user mode one. So, very fast overview on segmentation. You don't have to really understand too much of it, just the fact that it exists, and it's kind of based on how the OS handles where execution's coming from when you enter these interrupt handlers. So the int1 handler in Windows, KI debug trap or fault, it actually, I'll use my mouse pointer here because it's hard to use this thing. So I went too far. But anyway, you can see that there's a check on the code segment selector on the stack. And then based on whether you're coming from user mode or kernel mode, different things will happen. So if you're actually coming from kernel mode, you skip this code here, the swap GS and then the move R10. You actually skip all that logic and you go directly into here, which is the CLD. And that's because based on your mode of execution, GS means different things. The GS base means different things. In user mode, your GS base is your thread environment block. If you've done any Windows programming, you know that to be true for 64-bit Windows. And in kernel mode, it's not the thread environment block, it's your processor control region. It's whatever you're executing under. So if you're coming from user mode, so you've entered this interrupt handler from user mode, you actually need to swap to a kernel GS, right? How else is the OS going to access these kernel data structures and use that GS base? And the way it's done is by issuing this assembly instruction called swap GS, and that puts the GS base for the kernel mode data structures there, so that when you access GS 188, you're not reading user mode memory, which is under the control of a user mode application. I explained what swap GS did, but just an overview, all it does is it takes whatever's at that GS base, just like what was at that FS base, and just swaps that with this MSR, which is a model-specific register, a hidden CPU register, and it'll allow the kernel to then access the GS base to read kernel mode data structures. Pretty straightforward. Now Nick's going to explain how we leverage move SS and pop SS specifically to enter these interrupt handlers and confuse the operating system into actually thinking that we've entered from kernel mode and therefore avoiding the swap GS. And this is like the heart of the exploit.
Perfect. So Nemi kind of gave us a good high-level overview of segmentation and kind of the stuff that you're going to need to actually understand in order to grasp how this works. And need to remind you that there's a quiz at the end. So if you don't pass it, you're actually banned from Black Hat for life. Or that's what they tell me anyway. So if you look at the right, the assembly, if you're familiar with assembly, this is kind of going to be easy for you. So if you look at the top instruction, exclusive OR EAX, and then you follow it by increment RDI, after every instruction cycle retires, the CPU recognizes pending interrupts in a priority order, and that's defined specifically in the Intel manual. But there's a specific case where when SS is loaded, either via MoveSS or PopSS, until the instruction after it completely retires, interrupts are held pending. And in this particular case, what we were thinking is that it's best if you think of SS and ESP, as Nemi explained with segmentation, as combining themselves into a single stack pointer. So SS plus ESP would combine themselves to equal a particular linear address. And after SS, MoveSS or PopSS completes its execution, all interrupts are held pending until the instruction after it is finished. It doesn't matter what instruction is after it. It could be a branch, it could be any of the ones that you see above it. Complete its execution, no interrupts are going to be recognized after it. And that's kind of the heart of how this vulnerability works. And so how do we discover this? So Nemi and I kind of both work in anti-cheat. And in the anti-cheat space, lots of people attack our software with virtual machines. And the reason for that is it gives them it kind of gives them a high granularity of instructions that they can trap on and spoof certain instructions to give back information that would normally not be received by our anti-cheat software. And at the time, my thought was, and in the particular case, Intel VTX CPU ID is it's an unconditional exit. My thought at the time was, well, what would happen if you followed CPU ID and it followed a MoveSS load? What would happen if we had a VM exit after MoveSS? And in this particular case, Intel actually explicitly describes in their manual that, hey, during this exit, there's a blocking by MoveSS for one instruction cycle. AMD actually says nothing. It's like, hey, it's whatever. So just to dive into a deep technical detail for you quick, AMD, if we have a VM exit after CPU ID with a pending DB, it just completely throws it out. In Intel, it's actually held pending, and if the VMM developer wrote their code correctly, it will be thrown after the CPU ID increments its instruction by one complete cycle. And so to expand on that, my thought was, well, what would happen if we had a MoveSS and then a pending DB and then a branch? So what happens is if you have MoveSS or PopSS and it accesses memory followed by a branch, after that, right after that instruction, it fires an int1 right after that instruction. And what happens if we do an interprivilege interrupt? Okay, and the two ways that we can do that in user mode are with interrupt and Syscall. So if you look at the assembly at the bottom in the white, what's important here is that RAX is actually primed with debug registers. So if you've done at least some type of user mode Linux debugging or Windows debugging, you can actually set with the setThread context function on a linear address, we could say that RAX is going to fire an in1 after it accesses memory. Now, what would normally happen is after MoveSS accesses memory, if RAX was actually primed with debug registers, is it would fire an int1 after it finishes its execution. But as I described in the previous slide, in this particular case, and only this particular case, it's held off until after the instruction, after it completes. And this is an interesting case, because what happens if after that instruction we have an inner privilege interrupt? So I tried that actually one random afternoon at my house, and my machine just blew up. So what happens? We execute an int3 in the context of user mode. In Windows, this is not privileged. Okay, the DPL is actually a 3, so we can execute it without any type of issue. The int3 would normally cause a branch to the Windows version of the int3 handler, which is KI breakpoint trap. But since we have a pending int1, before it ever executes the first instruction of KI breakpoint trap, it's actually going to go to the Windows int1 handler, which if you're familiar with single-stepping instructions, it goes to the int1 handler after every single instruction is executed. So if we look at number 4, it's actually going to go to K debug trapper fault, which is the Windows name. It's actually the Windows symbol name for the int1 handler. And it's at this point in time that the Windows kernel becomes completely confused, because we're actually at execution at KI debug trapper fault, where it thinks it came from kernel mode, when in reality it came from user mode. So this is just a simple demo, and as I explained at the beginning, this isn't entirely critical. It's just a way to crash a machine. We're going to get to the actual cool shit later. So if you look, we have execute. It's wrapped in a try except block. This is just in case it crashes. So if you look at the bottom right, this is actually Nemi's code for our GitHub link. So if your machine was not patched for pop SS, this would actually crash your machine. And depending on the state of your machine at the time, you could get a blue screen, your machine could completely hardlock, it depends. But if your machine was patched, it's just going to throw an exception, and it's just going to cause an early exit. This is our assembly. I'm going to kind of walk you through this just a little bit. So if you look at the top, we do a move SS to the stack selector. That's important because later, when we do a move SS, it has to be a valid SS. If we don't load a valid SS, it's going to cause a GP fault, and our exploit's not going to work at all because it's going to cause an exception earlier than it should. And then if you look in the middle, kind of you'll see a call set data breakpoint. That's important because, of course, we have to have a pending DB exception by the time we reach the move SS. Otherwise, we're not going to have the pending DB fire at the wrong point that it should. And then, as Nemi explained earlier, we call the set thread context the higher level kernel 32 function. We just call that to set the data breakpoint on the move SS, the actual memory that it's going to access. That's important again because if it doesn't have the debug register armed, then this interrupt isn't going to fire. And this is kind of the heart of it. Again, it's nothing fancy. It's just going to crash your machine. So if you look at the top, we just have the move SS followed by an int3. So again, move SS is accessing memory, and the RAX, the D reference there, is accessing memory that is currently armed by a debug register, followed by an int3. So what happens is after the int3 finishes its execution, it's going to fire an int1. And this is a quick video representation of how this works, and Nemi's going to go ahead and walk us through this.
Yeah, so we'll step through this using the GDB stub, and we can actually debug VMware and see how it handles it. So specifically what we do is we start a timer just so that you can visually see when I break in to the debugger. We run the move SS sample that you just saw the code for, and you can check the GitHub link if you're confused about certain things. There's a spin lock there. I'm not sure if you saw that in the code, but this is just done so that I can break in at the point before we actually run the move SS int3. I can just patch this out to a NOP, and then we can single step through these instructions real quick using the hypervisor debugger of VMware. So the move SS is going to dereference RAX. RAX contains a hardware breakpoint primed upon it. Now, if this wasn't move SS or pop SS, it would actually cause an int1 to happen as soon as that instruction completed, but it doesn't because of the behavior of move SS. It suppresses that for one instruction. That means that that happens upon entry of int3. And now we execute int3. The hardware breakpoint hasn't hit. The hardware breakpoint is applied now after we've entered int3, but look at where we're at. We're actually at the int1 handler. We're at ki debug trapper fault. So we've entered the int1 handler, not the int3 handler as what we've expected. And if you look at the stack, actually, which I'll get to, I'll highlight that using my mouse. You see ki breakpoint trap is on top of the stack. And if you remember when I sorta gave that explanation on how the CPU reacts when an interrupt fires, it puts the previous state of the processor on top of the call stack at the point of the exception. So ki breakpoint trap is apparently the cause of the int1 exception, which is great because that means it's coming from kernel mode. It's actually coming from kernel mode even though we caused the behavior to occur from a user mode program. We ran an int1 from user mode, but we actually delivered it in kernel mode, and that's the beauty of the exploit. That means we've entered ki debug trapper fault with a kernel mode CS so that we don't do the swap GS that I mentioned would happen later. And you can see if we look farther down on the call stack, you can see where our user mode code fired. This was the int3 branch to the kernel. Also add stuff to the interrupt to the stack as part of the interrupt handling of the processor. And now if I resume the operating system, it's hosed. It's not going to continue at all. It's stuck at 8 seconds. And if I break in, I'll be stuck in a perpetual page faulting loop. So the machine is essentially not going to progress anymore. And if I keep breaking into it, you'll see that it's still stuck at that same point in code. So we have successfully caused the machine to deadlock by just executing 2 assembly instructions. Pretty crazy. So let's continue with that. It gets better because we can actually make that and use it as a weaponized thing. Instead of just hosing the machine, we can actually get system privileges, but we'll get to that later. So again, as I just explained, the whole beauty of this is that you avoid the swap GS. So there's no need to do the swap GS if you're coming from kernel mode. And we've looked at this code already, this test, which compares that code segment that's put on the stack when you enter an interrupt handler, checks to see if it's coming from kernel mode, and because it thinks it is, it skips this code. Now, because we control the thread environment block and GS is the thread environment block in user mode, and when we've entered this from user mode, we could overwrite parts of that thread environment block to cause the CPU to execute code wherever we want. But we don't want to do that because that gets a little more complicated. What we can do is we can actually just choose an arbitrary GS base, thanks to the fact that there's an instruction called write GS base that lets you set any address there. So when the kernel reads GS memory, it doesn't dereference your thread environment block. It doesn't dereference your processor control region. It actually dereferences memory that you completely control, and that makes it even easier to exploit as opposed to just overriding your TEB. So Nick's going to do a quick recap just to explain where we're at and what we have now.
All right, perfect. So if you were paying attention, basically what happens is we end up firing a DB exception at an entirely unexpected location. And operating system developers at the time, per the Intel and AMD instruction manual, were not prepared for this particular case. And the handler that they wrote, which would be the int1 handler, was not aware that the interrupt that it was currently handling was coming from an untrusted location. And so what happens is it's going to start using data that was sent to it that it thinks is kernel data, but in reality it's user mode data. And since, as Nemi explained, we control GS base, most CPUs to this day support the WRGS base instruction. In the event that it didn't, we can still send it user mode data from what's basically the user mode tab. It would just be substantially more difficult. And at this point, basically, we need to find instructions that are going to capitalize on this fact that we're using data that it thinks is kernel mode data, but in reality is from user mode. And at the very bottom, in the event that you might need a new prescription for your glasses, we want to turn this into some kind of profit. We want to weaponize this. So these are my initial weaponizing attempts. We're going to go through mine, then we're going to go through Nemi's over here. So at the very beginning, I erroneously assumed that there was no encoding for MoveSS RAX, which, as you can see, since it's surrounded in brackets, dereferences memory. I thought at the time that there was only a MoveSS AX, which is an immediate value, which is in the instruction stream. So if you're really actually familiar with how debug registers work, you would know that what you see there, the MoveSS AX, would not actually work as far as a debug register is concerned. It would not fire any type of int1. And this was pointed out to us in error by some of the Linux developers, thankfully later, after we released this exploit. But at the time, what's important is I tried to weaponize it through popss, because popss, if you're familiar again with assembly, pops data from the stack, it accesses stack memory. And so I tried, the assumption there is that popss is going to access stack memory, so if we arm it with the type of debug register, it's going to dereference stack memory and it's going to fire an int1. Unfortunately, popss in AMD 64 and Intel's version of a 64-bit code is not valid in their 32-bit compatibility code segment. And on Intel chips, Syscall is not valid. And the reason that that's important is we wanted to use a user mode stack when we execute Syscall. So at the time, I just focused on the int variant, and the int variant is basically we execute int, and we check the Windows int1 handler into using data that we pass it when it should have done swap.gs, but it actually doesn't. So if you look, basically our goal was to try and find some type of instruction that's going to use, or I should say, a set of instructions that's going to use GS. And if you see right here in the bug check function, and the reason bug check, if you're familiar with bug check, is actually a blue screen. KE bug check X is basically the initial function of starting a blue screen on the Windows kernel. It starts using RCX from data that is actually sent, that we send to it. So the goal is, hey, it's reading data. It's reading data from a GS that we send it, and hopefully it's going to turn it into something else. I mean, right now, as you can see by the highlighted instructions, it's reading it. But if it's just going to read it, we're kind of shit out of luck. We kind of have to hope that it's going to use it for something else. And in the actual function that it calls, you can see RTL capture context. RTL capture context. You see that it ends up writing data. And if you look carefully, all the instructions before the yellow highlight, it writes data to a pointer that we put in. So RAX, RCX, RDX, R8, R9, R10. Unfortunately, those are all clobbered during the interrupt dispatch process. And in our luck, the only register that we controlled was R11. R11 would be whatever we send it on input. So if we send on input to the exploit 0, it would be 0. If we send 1, it would be 1. And in this particular case, we wanted to attack GCI options, which is the code integrity variable in Windows, because we want to load a driver. But at the same time, we don't want to continue the bug check process, because that would completely destroy system state. And by the time we actually run kernel code, we would be in a situation where recovering the entire system would be very difficult. So if you actually look at the highlighted instruction, move APS requires 16-byte alignment. So we sent in a particular linear memory address that was not 16-byte aligned. So since it's not 16-byte aligned, move APS actually causes a general protection fault. And since it causes a general protection fault, it starts the entire bug check process all over, executing this entire process repetitively, spinning over and over and over. So what we have here is a write what where vulnerability that keeps writing the same keeps writing the same memory over and over repetitively. And since we have access to other CPUs, we can change the memory that it keeps writing to. So the goal here was to load a driver, obviously an unsigned driver. And without getting into deep technical detail, you can ask us later at the Q&A. CPU 0 has to do the driver loading. The reason for that is related to APIC priority type of interrupts. So CPU 0 would be the only one that could respond to disk interrupts. So CPU 0 actually had to do the driver loading, while anything other than CPU 0 could run the actual write what where stuff. So what that means is that this particular vulnerability requires more than one CPU, which in most cases, most computers today have more than one CPU on them. And we were stuck because CPU 0 would actually send down TLB shootdowns to the other CPUs. And we were kind of screwed because we didn't have a way to resolve the packet barrier pointer. And we were stuck. We had nothing we could do. Thankfully, by chance, Nemi discovered a
dumb luck.
Nemi didn't by complete dumb luck while just working on some random shit. Other than this, Nemi actually discovered a pointer leak to the KPCR. So we were able to resolve a pointer to the KPCR, and we were able to add that to our write what where spinning CPU, to add that to say that, hey, all the CPUs are done with their TLB shootdowns, and you can continue on with your execution. We ran into another problem where that CPU would run out of its double fault stack space, and that would flow into its KPCR. Luckily, his pointer leak also gave us a pointer to the TSS, and we were able to overwrite the double fault stack. In that particular case, we overwrote the double fault stack to point to user mode memory, and that completely solved that problem for us. So quick recap here. At the end of the day, this was really complicated. I spent, I would say, an entire month of my life trying to make this work, but at the end of the day, it worked. It worked really well. And that was the invariant. What we're going to dive into next is Syscall. And again, with Syscall, we end up using a user mode stack, executing kernel code. Nemi's going to walk us through that.
Yeah, it's much, 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 much easier because you don't have to deal with a lot of the complicated things that the int handler forces you to do. So the best thing about system calls, when they occur, they actually don't do a stack swap. So in the terms of the previous exploit, when we fire an int3, and then we get that pending int1 that fires afterwards, what ends up happening is because there's a privilege level change, we're going from user mode to kernel mode, we swap stack. Now, with system calls, that doesn't happen. Actually, as part of the syscall instruction, it's documented, well documented, that you're supposed to update the stack yourself. And you can actually see down here, this is the system call handler. So when a syscall fires, it goes into KI system call 64 on Windows. It does a swap GS, and then it loads the appropriate stack pointer on that CPU. Now, because we never actually execute any instructions in KI system call 64, we enter kernel mode with a user mode stack. And that makes it so much easier to exploit. So it functions very similar to int3, but better. System call executes in the context of a user mode code. It branches to the system call handler, which is KI system call 64. Before any instruction executes in KI system call 64, that means that swap GS doesn't execute. Before any instruction executes, that DB that we suppressed by move SS and pop SS fires, and we go to the int1 handler, which is KI debug trap or fault. And then that's entered with a kernel mode CS and with a user mode stack. Now we're going to go through the demo code that actually makes this possible. It's on Git, so you should really just check it out there. There's a lot of stuff here that happens, but a lot of it is just like boilerplate code that needs to happen. We need 2 CPUs for this exploit, similar to the int3 variant. The most important thing is we have to figure out where certain key locations of the Windows kernel are in memory. So we need to overwrite the driver signing enforcement check so we can load unsigned drivers. And then we also need to steal the system token so that we have admin privileges from an untrusted application. So what we do to do that, achieve that functionality, is we just load symbols using the Microsoft symbol server. So Microsoft has a public website where you can just hit up and contact and get symbols for your particular kernel version that you're running on. So as long as that box that we're trying to exploit has internet activity, we can just download symbols that are appropriate for your kernel version, touch these undocumented structures, things that may change per patch, and reliably exploit all the different kernel versions that exist. Furthermore, there is a little bit of ROP gadgetry that has to happen because nowadays there's a lot of security mitigations, especially in Windows 10, that prevent you from executing user mode code with kernel mode privileges. That's done through SMEP, Supervisor Mode Execution Prevention. That's inside of CR4, and we actually have to disable SMEP, and we do that by using these ROP gadgets that allow us to execute in the context of the kernel, disable SMEP, and then we jump to our user mode code to make it easy, because we don't want to stay in this return-oriented programming world forever. Furthermore, again, we get all these offsets through those symbols that we'll need, and we'll go over why we need those later. Finally, one of the last things that we do is we prepare the process. It sounds super generic, but because you're not running as an admin, you have no way of guaranteeing that Windows won't page out parts of your process. And if it's paging out memory inside of your user mode application that you need for your exploit to work, that like screws you over. So we make strong suggestions to the memory manager to be like, hey, try not to page out this GS base that we've allocated. Otherwise, we'll throw a page fault and then the exploit will get screwed up. And then finally, what we do is we set that hardware breakpoint, prime it on that location that moveSS will read from. We execute our ASM function, which will prepare the CPU and then start the core of the exploit. Again, this is going to be more or less stepped through in the next slide, so we won't go too much into details here. CPU 1, then we need two CPUs. CPU 0 executes the exploit. CPU 1 constantly probes stack memory that CPU 0 is executing under, and the goal is to override a return address that CPU 0 is going to return from, and then we're going to go into our ROP gadgets that we found earlier, which will then disable SMEP and jump to our user mode code. Finally, this will also be demonstrated later, so we'll just go to the video. That's necessary to re-enable SMEP and then restore the kernel back. So in our VM, we have this little batch file. All it does is it loads a driver and then starts it using the service manager. Very simple. We try to run this batch file from an admin command prompt, but we can see that it's clearly not signed with a valid digital certificate. There's a little error, and the machine isn't booted in test signing mode, so it won't accept this. So if we run this in an admin PowerShell, it says Windows cannot verify the digital signature for this file. It's not valid. It's not a valid digital signature. Now, if we try to run this from a PowerShell that doesn't have admin access, you don't even get to the driver signing check. It just says access is denied. You don't have privileges to even get that far. So what we do is we run the exploit first, and then we install the driver, and that should give us everything. So to get to how a lot of this works, we're going to break in, again, using that GDB stub that VMware provides so that we can debug the hypervisor. We break in a spin lock similar to the denial of service proof of concept. I'm going to load symbols for my exploit just so that it's easier to read what's going on the screen. Shouldn't take too long. And then we specify that address, the base address of where it's loaded into memory. We're going to knock out this jump like we did for the previous example so we can progress. All right, so now we set the GS base to whatever we want. In this case, this is our GS base that's under our control. We run moveSS, and then we enter using Syscall. So what should happen is we should go to the system call handler, but because of KI debug trap or false behavior, we get thrown into the int1 handler because of the moveSS behavior. And you can see that we're coming from KI system call 64. And this means that now we're assuming that we're coming from kernel mode. So when we access this memory, this GS memory that we're touching all over the kernel, it has to be valid. And that's part of what our exploit does. Our code exploit has to set up this GS memory to be valid. And all of this is under our control. Everything that touches GS is directly under our control. Eventually, we get to the dispatching of the exception. And then we choose a return address on the stack to overwrite, and we chose an arbitrary function later on during exception handling that CPU1 will overwrite. And in this case, the function that we chose is KE context from kframes. And you can see at the bottom of the stack, we've actually overwritten the return address to go to our ROP gadget that we found. Now, you can see on CPU1, which I just swapped to, you can see that stack pointer points to that memory that we just overwrote on CPU 0. So if we go to CPU 0, you can see that's the same address, and you can validate that by looking at the slides later and the video later. Finally, this function's pretty big, and that's why we chose to overwrite its return address, because it's long, and that's the goal. Like, hopefully it takes a while to execute so that we are able to overwrite it on CPU 1. Lots of XMM operations. Eventually, we will do a return to get out of this function, and then we go into our ROP gadget. Our ROP gadget does a big stack change. So we do that massive add RSP so that we don't have bad memory to work with. We load CR4 with the value that we choose to disable supervisor mode execution prevention. And then we return out. And finally, we're executing our payload. So in user mode, as CPL0, we are setting up a way to come back and recover the operating system. We steal the system token from the system process so that we have admin rights to load the driver. We disable driver signing enforcement to get past that second barrier. Finally, we set up the IRET stack so we can return back to our user mode code. We re-enable SMEP, and we're in user mode. We're back in our program. We're going to hit play, and we're executing under NT authority system. And now we'll run the driver, and we'll actually load it. There's no error message anymore. We have ring 0 privileges. And the machine is popped. Cool. So I don't have a lot of time left, so I'll go over this really quickly. A lot of this was patched in May. Microsoft Research did MSRC did a really good intercompany, as well as reaching out to other OS vendors that were impacted by this. So shout out to them to helping coordinate a lot of these fixes. They fixed a lot of these problems in May. I think most operating systems should be patched now. They followed the suggestion that was made in our white paper, so you can check that out. I guess the magic is that the KI debug trapper fault now will use a known good stack regardless of how you enter it. Even if you enter it from kernel mode, it will use a known good stack, just like the double fault handler. That means you can't abuse Syscall anymore. And furthermore, GS memory is never dereferenced until you're known to be in a good state. And the way you're known to be in a good state is by checking KI debug traps. And KI debug traps is basically an array that contains function pointers that you could enter from user mode, and the goal is if you throw an int one from any one of these, you're not allowed to progress, and you just IRET out, so it avoids that exploit. Now Nick's going to wrap it up with some shout outs to some industry folks.
All right, so we have a couple of shout outs we'd like to give. Alex Ionescu, I don't know if he's out there, maybe you are, maybe you're not. He actually named our exploit, why so Spurious. I think it's appropriate. I actually think it's a pretty cool name. And then Jan Baluk, he did weaponizing on the int variant. It's actually really cool. He did it much faster than I did. So you actually see the link here to his blog and then to his weaponizing work. It's definitely some cool shit there. You should check that out. And then, so what are some lessons we learned here on how to do bug bounties? So you have to have a really cool name for your exploit. Maybe you want to get that off a Lego's box for ages 6 to 12. Maybe, I don't know, like Spectre, Meltdown. You know, come up with a cool name, and then you might want to pay a graphics designer to come up with some type of graphic for your vulnerability, because apparently that's the thing today. And then you also want to have a great soundtrack for your vulnerability. All the vulnerabilities have great soundtracks these days. Definitely want to come up with some good music to hype your vulnerability. And then last but not least, WorldStar exclusive. I mean, if you're not WorldStar exclusive, it's not a good vulnerability at the end of the day. Thank you.
That's our logo. That's the white paper. Like, retweet, and subscribe.